So, good morning, students. So, yesterday I have discussed a problem regarding this link. So, I'll move on to the next problem. So, I have discussed this problem, I think so. Design of a spindle of a milling machine. If it is so, I'll skip this and I will take one more problem. This one. Any one of you just read the problem? Tejas, Tejas M. Tejas M. Are you there, Tejas? Read the problem, Tejas. Tejas, read the problem.
A bar of 50 diameter. Find the one end of subjected to torsional load 1 kilonewton in addition of the axial pull of 15 kilonewton. Determine the principal stress if the length of the shaft is 250 mm.
Okay. So determine the principal stress. See, this is a bar, okay, subjected to an axial force of 15 kilonewton and a torque of 1 kilonewton meter. See, similar kind of problem we have did here. Have I solved this problem previously? Any one of you? Have I discussed this problem? If not so, I will discuss this. Okay, fine. See, so this is a bar having a diameter of 50 mm and a length of 250 mm, and it is subjected to torque 1 kilonewton meter. In addition to that, it is subjected to an axial pull of 15 kilonewton. Okay, so this is somewhat combined loading. The shaft is subjected to axial and also torsional load. So this case of problems we call it as combined loading problem. Whenever a body experiences more than two types of loading, so that condition is called combined loading. Clear? So you have to find a principal stress. See, whenever a body experiences combined loading, so you have to find out the principal stress in it. Okay, so in order to determine the principal stress, I have to calculate the stress induced due to axial load and also the shear stress induced due to torsional load. So then using those two values into this standard formula, I can calculate the maximum normal stress and the minimum normal stress. Okay, so like this. So now I will calculate the direct stress, that is the normal stress. Direct stress or normal stress, it is given by sigma is equal to force by area. So it is subjected to an axial force of 15 kilonewton. So then sigma is equal to, just use this formula, force by area. So area means this is a circular cross section. How it is circular. So they have given that this bar is having a diameter of 50 mm. So it means that it is circular cross section. So I will use this area formula and I'll calculate the direct stress, normal stress or axial stress. So it is tension 7.64 megapascal, that is tensile stress. And also, this body is subjected to twisting moment, torque of 1 kilonewton meter. So a shear stress is induced. Okay. So I can calculate the shear stress tau is equal to, using this formula, torque equation, T by J into C. Using the torque equation, I'll get this formula. So substitute this. So I'll get a shear stress of 40.744 megapascal. Clear? And maximum normal stress. See, in the compound stress chapter in mechanics of material subject, so there we have derived this formula, that is for maximum normal stress and minimum normal stress. Okay, so formula for maximum normal stress is sigma 1, minimum we call it as sigma 2. So sigma 1 is equal to sigma over 2 plus square root of sigma over 2 square plus tau square, where we have calculated the sigma and tau here. Tau is the normal stress 7.64, and sorry, sigma is the normal stress 7.64, and tau is 40.744 megapascal. So just substitute these values into this formula so that I can calculate the maximum normal stress and the minimum normal stress. Okay, and ultimately you can calculate the maximum shear stress using this formula. So I will just give you 2 to 3 minutes of time. You calculate all this, that is maximum and maximum and minimum normal stresses using this standard formula. All of you calculate it. Just check it out whether the answer coming out over here is in par with the formula. Okay, is the screen visible to you? Hello, any one of you answer me? Is this scan copy visible to you?
Yes, sir.
Okay, fine. Have you calculated the value maximum normal stress? See, unless you calculate yourself, the subject you cannot learn, because this is purely a problematic one. So simultaneously, you should calculate the values along with me. Then only you will get familiar with the formulas, steps, and the data handbook formulas. Okay. Sigma 1 got a value of 44.74 megapascal, that is a tensile. Suppose if this value is negative, it indicates compressive. And I'll find out the minimum stress. Only the difference is here it is positive for maximum and negative minus for minimum. So I'll get minus 37.1 megapascal, it is compressive. So this is the minimum stress induced in this body due to the axial force of 15 kilonewton and a torque of 1 kilonewton meter. Clear? And the shear stress you can calculate using this formula, square root of sigma by 2 square plus tau square. So maximum shear stress induced in the body is 40.92 megapascal. So very simple problem. So this may be asked for 6 to 8 marks in the examination. Okay, this is combined loading problem, combined loading problem. So whereas this problems, it is just a single loading. Here it is purely subjected to twisting moment. Okay, so where you calculated the torque and you have make use of the torque equation to determine the one of the geometry, that is outer diameter, and in turn you calculated the inner diameter. So this is a problem where a specimen or a body is subjected to one kind of loading, whereas just now we have solved a problem where a body is subjected to more than two type of loading. So here it is axial loading and here it is a torque twisting moment loading. So what happens? You have to calculate the stress induced due to axial load, and later you calculate the shear stress induced due to torque T, and you have to combine both the values in order to get the maximum normal stress or minimum stress. Okay, so for that we have a formula. This is taken from the compound stress chapter in the mechanics of material subject. Okay, just recall it. So where we have you have developed, you have derived this formula with regard to the maximum normal stresses and minimum normal stress. So then ultimately determine the maximum shear stress. So with this, I will move on to the next problem. Okay. So one more kind of problem. Hmm. Nandish HU, are you there? Nandish HU. Nandish, just read this problem statement. Nandish, read this problem statement.
Sir, sir.
Read this problem.
Okay, sir. A 50 mm
Just
diameter.
read this problem.
Okay, sir. The a
Uh,
50 diameter steel rod supports a 90 kilonewton load, and in addition is subjected to
not,
a
not 90 kilonewton, it is just 9 kilonewton.
okay, sir, 9 kilonewton load, and in addition is subjected to the torsional moment of 100 newton meter, as shown in the figure. Determine the maximum tensile and maximum shear stress.
Okay, okay, thank you.
Okay, sir.
So it is one kind of typical problem. Okay. So here it is it is a body diameter of 50 steel rod. This steel rod is subjected to a load of 9 kilonewton. It means 9,000 newton, and also it is subjected to a torsional moment torque of 100 newton meter. Okay. In addition to this axial force 9,000 newton, it is also subjected to torque. It is as like a previous problem. Okay, similar to the previous problem what we have solved, but the difference is this axial load 9 kilonewton, it is not along the axis of the body. I mean the steel rod. Okay, it is acting at a point at a distance of 28 from the axis of the steel rod. So some kind of eccentricity is created over here. So this length 28, this distance 28 is taken as E. So eccentricity means the load, the point of load is not along the axis, but it is offsetted as for certain distance. So that is called eccentricity. So in this case, you have to determine the maximum and the maximum tensile stress and the shear stress. The problem is almost similar to the previous one with some modification. Okay, we'll see that. So this body definitely experiences direct stress. Along with that, it experiences bending stress. Anyhow, bending moment is not being applied over here, but this force, which is not on the axis, it is offsetted for a length of, for a distance of 28 mm. This force creates a bending moment on this steel rod. Okay, so just by taking the normal stress is not sufficient. In addition to that, you have to take the effect of bending moment due to this force 9,000 Newton. And this bending effect, bending moment, or bending stress induced due to this bending moment can be calculated using this formula. This is taken from bending equation. This is taken from bending equation where sigma is equal to mb by I into c. Okay, so the combined stress due to this 9,000 Newton load, it is normal stress, that is F by A, plus bending stress. So this 9 kilonewton will have two effects. It creates a direct stress, that is F by A. In addition to that, it will also create a bending stress that is given by MBIU into C, that is taken from bending equation. Okay, and this moment is calculated here. F into E, that is force into perpendicular distance. F into E, that is the moment, and due to this moment, the stress induced is called bending stress, or it is also called as flexural stress. Okay. So now I'll calculate the combined stress. So that is given by F is sigma is equal to F over A plus MB by I into C. We'll come to this torque later on. Okay, and find out the combined stress. So just put that value 9,000 Newton over pi by 4 into d square, that is 50 square diameter of the rod, plus bending moment 9,000 into 28 divided by pi by 64 into 50 to the power of 4 into the C. What is the C? C is the distance of the extreme fiber from the axis. So this distance from the distance of the extreme fiber from the axis. So it is nothing but d by 2. I mean 50 by 2. So calculate the sigma. So it is 25.12 megapascal. That is tensile in nature. If this value is negative, so this indicates the stress induced, normal stress induced is compressive. Whereas in the previous case problem, we have not calculated this bending stress. We have not added this bending stress with the direct stress. Why? Because the load was acting along the axis, it would not create any bending moment at all if this 9,000 is acted on the axis. In this case, it is acting at a distance of 28 mm from the axis. So that's what this 9,000 Newton creates direct stress, plus it also creates bending stress. So combined stress, we call it as combined stress. So combined stress is 25.12 megapascal. Then we'll come to the shear stress purely induced due to this torque. So always remember that torque induces shear stress in the body. So I am going to calculate the tau using the torque equation. So recall the torque equation, and tau is equal to T by J into R. Okay, so just like similar to bending equation, so recall the torque equation. Torque equation tau is equal to T by J into R, where J is polar moment of inertia. So in case of bending moment, where this I is area moment of inertia, that is pi by 64 into 54, this is area moment of inertia. And whereas this one, J is polar moment of inertia. And always you remember that polar moment of inertia is addition of area moment of inertia in x direction plus area moment of inertia in y direction. So pi to the power of 64 pi d to the power of 64 plus pi to the power of 64, it gives you pi by 32 into d to the power of 6 d to the power of 4. Okay, so this is polar moment of inertia, and this is area moment of inertia. This is area moment of inertia, and in case of torque, this is polar moment of inertia. So I am going to calculate the tau. So tau is 40.074 megapascal. Yeah. So soon after determining this shear stress, so you have to find out the maximum tensile stress and the minimum tensile stress, and also the shear stress. Okay. So in the problem, what is being asked? So it is being asked to determine the maximum They have not asked to calculate the minimum. So we'll just find out the maximum tensile and maximum shear stress. So look at this. So same formula what we have used for previous problem. So just to put that sigma value, combined stress value over here, and the calculated shear stress value, that is 4.074, and determine the maximum normal stress, that is 25.76 megapascal. That is purely tensile force, tensile stress. And also find out the maximum shear stress. So using this formula, tau max is equal to square root of sigma by 2 square plus tau square. So after substituting all this value, we'll get the maximum shear stress. Very simple. Okay. So only thing is you have to analyze the problem, apply your mind. So just you have to compare this problem with the previous problem so that you could able to differentiate the problems and apply the mind accordingly and solve the problem. That's it. Okay. Shall I move on to the next problem? Is there any doubt with this problem? Let me take feedback about this problem. If you have any problem with this, any doubt with this problem, I'll spare some time for that. If no, I'll move ahead. Okay. So next problem. Okay. Any one of you read this problem? Who is going to read this problem? Prasad MS. Prasad MS.
Yes, sir. Yes, sir.
Read this problem.
A circular rod of 60 mm diameter is subjected to bending load and torsional load as shown in figure. Determine the nature of magnitude of stress at the critical points.
Okay, good. So just analyze this problem. How you can relate this problem to the previous problems. The only thing is we have solved a problem where this bar is subjected to torque of 3 kilonewton meter, where earlier problem this force was on the along the axis. Now this force is acting at one end of the bar, okay, 5 kilonewton. So definitely one can say that in addition to this shear stress induced due to the torque, so this 5 kilonewton purely induces bending stress. This 5 kilonewton purely induces bending stress, and this bending stress is maximum at these critical points A and B. So I have mentioned over here as a wrote, the shaft is subjected to bending and torsional load, and the critical points are A and B. It means that maximum bending stress is induced at A and B. Say A experiences tensile stress because when you apply load in this direction, this beam tends to bend like this in downward. So this point A experiences tensile, where point B experiences compressive. Okay, so calculate this bending stress due to this 5 kilonewton, and also calculate the shear stress due to this torque applied, that is 3 kilonewton meter, and find out. See, they have asked you to determine the nature and magnitude of stress at critical points. So I can say critical points over here. This is critical point A and B. What are these critical points? Critical points are the one where the stress values are maximum. And from that point, the metal failure or the material failure takes place. So those points are called critical points. So now we have to calculate the nature and magnitude of stress at these two critical points, at A and B. So considering critical point A, we just calculate the bending stress, and put those value. Bending stress means nothing but the stress induced due to bending, and shear stress is stress induced due to torque. And put those values at A and B, considering at A and B. So look at that, considering B. So it means that at A, the stress induced is positive, that is tensile stress. At B, stress induced is negative. So just we'll see that. Okay. So the critical points are A and B. So I will calculate the bending stress first using the bending equation MB by I into C, where I is the area moment of inertia. So put those values. M is the moment, 5 kilonewton, 5 into 1000 into span is 300. This distance is 300. 300 divided by pi to the pi by 64 into 6 to the power of 4 into C is the 60 by 2. So diameter is 60. What is this C? C is the distance of the extreme fiber from the axis. Substitute all these values and calculate bending stress. So this bending stress C is tensile at point A and compressive at point B. Clear? And also calculate the shear stress using the torque equation. So the stress is coming out to be 70.736 megapascal. That is same on both at point A and B. And considering the point A, considering this point A, so maximum normal stress at A is given by this formula, same formula what we have used earlier. So make use of the formula. Positive means plus, maximum means plus, minimum means minus. So I'll calculate the maximum stress induced at point A, 114.45, that is tensile, and also minimum. Just I'll modify this formula with the negative sign. I'll get minimum stress induced at point A, that is compressive, and also calculate the shear stress. So tau max is equal to the same formula what I have used earlier. So I have calculated the shear stress. Similarly, what happens? The same steps to be repeated considering critical point B. So only the difference is this value, no, 70.36. This is positive for point A and negative for point B. Why negative for point B? This point B experiences compressive stress due to this load, 5 kilonewton bending load. So this lower portion experiences compression, upper portion experiences tension. So this B will consider this value as negative. Clear? So same procedure to be repeated with negative sign. Wherever you have 70.736, replace it negative. Shear stress remains same for both. So this tau value is same for both, for at A and B. See, look at, I mentioned it. Tau is without the 70.736 for both the cases, point A and point B, whereas this bending stress is different for point A and point B with sign, okay, positive and negative. So now I'll give you 5 minutes time to calculate the maximum normal stress at point B, the maximum and minimum normal stress at point B, and also maximum shear stress at point B. All of you just calculate it. I'll be back in 2 3 minutes. Huh. Did you get the answer? Same answer what I have discussed over here, displayed over here. Just verify the answer. So for at point B, the maximum normal stress is 43.72 and minimum normal stress is minus 114.45 compressive stress. And shear stress is this much. Tau max is equal to 79.08 megapascal. Clear? Okay. So the time is, we are running short of time. So I'll end the session at this stage. So we'll take up few more problems related to this in the next class. See, if you have any doubts related to all these problems, so let me know. Okay, you can send your doubts through WhatsApp or through email or through group what I have created for your class. I will try to answer it. I believe all of you have given attendance through chats. So 32 have submitted. Fine, I will end the session. Meet you in the next class. Thank you.